thank you for being here and contributing to the international exchange. So enjoy the conference on the 2 days we share together today.
Thank you, Big Boss. I then will invite another Big Boss, the founding chairman of the International Conference of Energy Storage and Saving. He's also the editor-in-chief of the journal who has the same name, Professor Wang Qiuwang from Xi'an Jiaotong University. Please.
Thank you, Professor Xiaofeng. Good morning, ladies and gentlemen. It's my great honor to be here. Actually, now is the best season in Paris, and you can see the hotel is very expensive here. So why? Because this is the best season. It's very comfortable and also very beautiful Paris, romantic Paris. Hope you enjoy, and everybody. I would like to take this opportunity to welcome all participants from around the world to join our international conference on energy storage and saving. And you know, as the founding chair of the ISENS conference, on behalf of the our university, Xi'an Jiaotong University, and also, you know, the honorary editor-chief, professor and academician, Professor Wenchan Tao, originally should come to on site to join us, but unfortunately, because of some visa issue, so he has to give up, and he will give the presentation online. And you know, I would like to sincerely thank all of you, researchers, students, and also the professionals, and also Ms. Tao from Wuxi, it's from the industry, for your participation and contribution to the growing international community. And after 3 editions, you know, this is the 4th international conference. The first 2 in Xi'an and the 3rd one in Qingdao. It's truly exciting to see the conference expand to Europe, the beautiful Europe, this time, and where the new idea and the partnership can grow. I would especially like to thank the local committee, organizing committee team at the University of Paris City and the Paris Interdisciplinary Energy Research Institute for their excellent work in making these events possible. ISENS conference is built on the belief of international cooperation and knowledge exchange are key to advancing sustainable energy solutions. I hope this year's conference will inspire you, connect you, and open new paths forward. Thank you again for being part of ISENS 2025. I wish you all a successful conference and an enjoyable time in Paris. Thank you very much.
Thank you, Professor Wang. Yes, we have chosen the right place here. It's the former medical buildings of the university. So it's one of the oldest buildings of the university. The big room, grand amphitheater next to here is a former room for anatomy, you know. That is a place that you open the body of a patient and you teach medical students how to make surgery, operation to find a treatment to patients. So today we're here. I think nobody will be lying on the table, no worries, especially for the plenary speakers. You are safe. However, I do think we can consider that we have the planet on the table, and we're trying to find a way for new, more sustainable solution for the planet. Because you know that we have the problem of climate change, and we know that CO2 emission is a serious problem, and we know that energy system is the main emission source of CO2 emissions. So that is why you're here to study about energy saving technologies. We also have the new phenomenon of renewable energy. You probably have heard of the blackout, the cut, electricity cut, power cut of Spain and Portugal in 2 weeks earlier. And that is probably due to a major problem of renewable energy. So energy storage is also another big block of solution that we need to discuss. So that is why you are here. We have received more than 110 submissions. We accepted 70 oral presentations and almost 20 posters. So we have invited 7 plenary lectures, and we also have 10 keynote speeches. We tried our best to make everything physical, but we still have several online, 2 or 3 online presentations due to visa problems or other issues. So this is the program. You all have example of this program. This morning we will have 2 sessions and 4 plenary conference. We will stay here probably for the whole morning. And we have 30 minutes coffee break at around 11 o'clock, and then we have lunch in the same place where we have the coffee. And during the afternoon, we will separate into 2 parallel sessions, one in this room, another one will be a big surprise because I don't have any solution right now, as the big room doesn't work now. So I will tell you, I hope that I can tell you at 11:30, before 11:30 about the other room. And we will have a cocktail dinner right at the same place this evening. Tomorrow morning, we will return here, turn back here in the same place. Also 2 parallel sessions. No, we begin by 2 plenary lectures first, and we have 2 parallel sessions. In the lunch, we will have a quick lunch because we need to move to another campus, which is around a kilometer from here. So if you walk fast as me, it takes 8 minutes. It can take a little bit longer if you are slower. The advantage is that we will try to make you discover another style of building, another complex, and we will separate in 3 different parallel sessions for tomorrow afternoon. Once we finish these parallel sessions, we will have the closing ceremony and also the last plenary lecture from Professor Liu from Hong Kong. And then we need to walk again. We need to walk to a boat, which is around 1.5 kilometers. And you can walk along the Seine River. So I hope that it don't rain tomorrow. That is I need to check every 10 minutes, the time. So several of you, especially students, didn't choose the gala dinner option because it's kind of expensive, I understand. And fortunately, we found a sponsor, we found a strong sponsor who would like to pay for everyone. So every one of you, you are invited to vote tomorrow. Yeah, this merit. So yes, we have 3 different sports. And now we are in the middle, and tomorrow we're going to the spot on the left one, sorry, and we'll finish the day on the right photo here on the Seine River. Yeah, this is, I will show you again later for the working thing. So we have a lot of partners, we have the lab, we have CNRS, we have Circle U, we have the Faculty of Science of the University of Paris City who give me a strong support to the conference. We have another engineering school, EMT, in Europe, who supported also the conference, the journal Energy Storage Saving. We have an alliance that we established with Guangdong last year, and they also supported our conference. We have a very strong sponsor, Wuxi Chemical Equipment company, who will make the fourth presentation, the last one for the morning. And we have this journal, research journal, who sponsored the gala dinner for students. So we will try to kick off. The very first part will be two plenary lectures, one given by Professor Antonio Cisternino from University of Pisa. He's specialized in computer science and data center management, information, and so on. And we have a second one from Professor Tao Wenquan, who cannot join us physically. And because he's more than 85 years old and he has more than 50 years of experience in heat transfer research. So that one will be on VSU, and then we will have 30 minutes discussion here between Antonio and Professor Wang, who will represent Professor Tao for the discussion part. So you may have noticed that this is a joint event between the ISENS conference and Circle U. Circle U is a European University Alliance composed of 9 universities. So you probably noticed that we have the broadcasting and the registration at the same time, because we have also more than 150 online participants from 8 other European universities like Humboldt University of Berlin, from University of Vienna, and King's College London, and many other, Pisa as well. So that's why Antonio is here. So I guess I can kick off with this time. Okay. Please, Professor Cisternino from University of Pisa.
Good morning, everyone. Let me check this. I think I'm gonna share the wrong thing. Oh, French. To disable the presenter view.
This one, right? No.
It is presentation. No, there is.
You think that? Okay.
Yeah, but I think that remote.
So that is why I didn't want to.
I think is this. There we are.
I'm on presenting. Especially.
Okay. So good morning, everyone. Thanks for inviting me. So this morning I will introduce basically the relation between software and energy consumption. It's a super hot topic. Everybody is talking about how many gigawatts or liters of water are needed to serve AI requests. Recently, Sam Altman, the CEO of OpenAI, communicated that they're spending a lot just to answer to the artificial intelligence, lots of computing cycle. And everyone thinks that this new technology, which is clearly disrupting in many ways, is also posing new challenges in terms of building facilities and being sustainable on the long time. I mean, we were at the coffee break, we were discussing, it's true. So according to OpenAI, they have more than, I think, almost 500 million users per week. but it's true that many users are not using so intensively this technology, and what will happen when this will be the case. And we all are using this, and already after just 2 years, we're living in a world where you can run a deep research that has become a common term that for us academics is beautiful, because actually you pose a question and you get this agentic AI going around and for 20 minutes processing information and give us summaries, which is beautiful, but it's also expensive in terms of resources, because we're moving from a world in which the AI is something interactive into a world where AI is agentic, is running in background, and this will increase the pressure. So, software and hardware have always been connected. I mean, it's fairly obvious to some extent, but the reality is that now is becoming really important. Software is the soul of the data center, is managing the data center. In the last 10 years, everybody's speaking about and talking about software-defined data center, because the data center is not something just a bunch of hardware and fans, but also sensors and software that regulates and try to optimize resources so that you don't, in the beginning, you were not spending too much. Now, it is also about sustainability. So we built as a university one of the largest data centers in the universities in Italy in 2016, which may seem not that far in time, but last year we doubled down because we were already hitting a lot of limits in our data center facility for running AI workloads. In particular, these years, are the years in which we are transitioning between air cooling and liquid cooling inside server technology, which is a big shift. When I attend supercomputing, which is the largest supercomputing conference worldwide, it looks like you go to the plumb shop. I mean, you find a lot of pipes, valves, and these kind of things that are very far from the typical electrical printed circuit board I was using to. So how can we measure this impact? There are a lot of numbers that are announced these days, but it's a difficult task. And we will try to have a look at what is the state of the art and just have some idea on how these things are made. And of course, how can we optimize things? And there are multiple answers to this question. So, first of all, the data center. So this is our data center. It's a building. It's outside of town. We started building real data centers around 2013 in Pisa. But quickly we found out that in town, Pisa is a medieval town, so it's complicated. We quickly hit a number of boundaries. First was energy. I mean, the power lines inside the town weren't designed to sustain the workload, but also noise, because when you go and heat a lot, you need to chill down things, and you need compressor system, and this is noise. And so that was unexpected, but we got some legal action from people complaining about the noise of the shielding system. So we had to move outside of town. So now we got this fairly big building, and this is basically the first part of the data center that was implemented in 2016. So it is based on 66 racks. We're running about 600 servers, 25,000 cores, 12 petabytes of storage, and high-speed network. So 400 gigabit on the Ethernet side, 800 on the InfiniBand side. And we will see that this is one of the reasons because we want to have more and more density in implementing these things, because one of the bottleneck is the communication. So in electronics and in networking, if you make things closer, you get better bandwidth and smaller latency in the communication. And now that we are running huge models, we will see what a model is very quickly. And so you have to load huge amount of data and process quickly using big matrices. And so for this reason, there is a big push in making things smaller and concentrated. So just to give you a number, which is relevant in energy, this data center was designed with a target of at most 15 kilowatts per rack. So the rack is where you store servers. We have 66 of them. And the design of this thing that was state-of-the-art less than 10 years ago, it was 15 kilowatts per rack. Today, with this design, if we install an NVIDIA server with H100 GPUs to make AI, it's basically an empty rack because it's 15 kilowatts just the server, okay? And what is a reasonable design today? At least 30 kilowatts. So factor of 2 in less than 10 years. And this is already worrying. So if you consider that beginning of 2000, the design was 3 kilowatts per rack, okay? So you see the progression. And in fact, if I look at the state of the art is up to 178 kilowatts in a single rack, which is complicated. It's complicated because also for us as a universities, it's complicated. How far we can go and support these kind of infrastructures, for how long? I mean, this 178 kilowatts in a rack means that a couple of racks and you basically exhausted the finance capacity of a medium or large university just to cover the cost of the current. So this thing is becoming, for these reasons, a game for very few players that can afford huge amount of resources. And this poses a lot of questions also in terms of research, because how can one experiment and have access to design that are secrets and not really disclosed? Nevertheless, we run basically 3 services in this facility: private cloud, virtual machines, HPC, scientific research, and of course AI, and storage, because you have to store data to process. And this thing was designed to be really efficient. I know that the next talk will talk about the power usage effectiveness, which is the 1.05. That's a very good number. I mean, large data center typically are considered good below 1.2, and it's basically the ratio between the total data center energy divided by the IT energy. So ideally, you will like to have 1 every watt is going into IT system. Actually, it's impossible because you have to chill down things. So this implies that you need fans and so overhead. And in any case, whether you're producing using, I don't know, solar panels or you're paying for energy, in any case, it's a good design principle to keep the PUE low, because it has several implications beyond the energy. I mean, the more energy, the more risk of fire, the less density you can use, and several other things. So we designed this, in fact, it's called Green Data Center because it was designed to be sustainable. And we use a closed circuit. So when you chill down things, you have basically 2 options these days. One is you use a closed loop of water. You chill down the water. You may use adiabatic cooling if you're smarter, but nevertheless, it's a closed loop. So you fill the tank, very little water dispersion. A lot of problem with the kind of water and clean the water, because when you circulate water, then you may incur in a lot of problems. But anyway, that is clearly okay for the design we made. It's sustainable, but you can draw not that much heat as it will be needed by a hyperscaler data center. So hyperscaler data centers are using a different approach, which is open loop evaporative. So basically, you build, let's say, either a tower or a lake, you circuit the water, and you use evaporation as a really efficient way of dissipate energy. But you are basically making evaporate 80% of the water in the worst case, which leads to the scarcity of the water resource, which is considered today in the hyperscaler the real bottleneck. Because with energy, we can try to go sustainable with wind or solar or nuclear energy. And in fact, it's known that many hyperscalers are looking into nuclear power to power data centers. But the water is, especially clean water, is finite. And in fact, North America is already in crisis. People is looking for South America to establish new data centers because the water is the current bottleneck of the thing. On the other hand, the closed loop, it will require too much energy, and this will unbalance in another way. So we expanded. Of course, we were having enough room. We had included 38 additional racks. Notice that basically we didn't go for to double down to another 60 racks because with the increased density of power, it's pointless to have so many space because the space will correspond to an expense in terms of energy you have to pay. So we had to expand the chilling system. But probably the most important thing is that we introduced air cooling and air-to-liquid cooling. So basically, we targeted, which for a university is reasonable, we target an hybrid infrastructure. It's been one of the first in Europe of this kind, in which basically we use the chilled air in the computing room to chill down a smaller loop to cool down the servers. And so basically, it's interesting even in the management of this technology. So basically, in the back of the servers, usually you have network power and that's it. So the cabling is it's very standard. Now you have these red and blue cables that actually are bringing water. So that's the circuit. The blue is bringing the chilled water, and the red is taking away. And it's complicated, even the management of the cabling. And inside the server, you have two more pipes, and the liquid is going around, which of course poses a lot of problems because, I mean, water is cheap. In fact, there are also other solutions for liquid cooling that we study, such as, for instance, the use of glycol and other liquids other than water, but water nevertheless is cheaper, and so if you want to go big, it's the reasonable way. But at the same time, if you get a spill and you're absorbing 30 kilowatts, that's a fire for sure. So you also have to pay attention also to the security of the facility. So this push has been mostly made by AI.
There's a magic hand somewhere. So please, you can just come back. Someone is sharing at the same time.
Okay. And disrespect, I know how to. Thank you. Okay. So most of this thing is for supporting AI. Why? So in general, when you increase the density, you tend to to lower the latency, so the time two separate components of the system will take to communicate, and this is crucial when you have to perform very large computations in which portion of your data are residing on different parts of the system. So typical, this kind of computation that are very typical in high performance computing community have a cycle of computation, then communication, then computation. So the smaller the latency, the shorter the computation is, okay? And so that's one of the reasons. And the other one is the bandwidth, so the amount of data you can transfer from one part of the system to the point in which modern servers using the GPUs use a proprietary bus designed by NVIDIA, which is called NVLink, and that basically ensures a huge bandwidth, which is much larger than the state-of-the-art of the network bandwidth. Okay, so you can top up 1 terabyte per second, which is 8 terabits per second, which is a huge amount of volumes of data, which is essential to process the AI models. Okay, so on the right you see two views of the same data, basically, and from which you can appreciate. So this is an air-cooled 8 GPUs server. And as you can see, you go up to, I mean, around, in the average, you are around 2 kilowatts. The liquid-cooled 4 GPU server, so you have to multiply by 2, is much more stable in the way it delivers performance. And if you multiply by 2, actually, you are using less energy than just one air-cooled server with 8 GPUs inside. And of course, with the 4 GPU, I'm powering more CPUs. And so an 8 GPU liquid will be even lower. The GPU costs a lot. So this is an air-cooled, no GPU server. So you see the progression. GPU is a huge impact in terms of heat and energy, and this means that as soon as you need GPUs, and for AI you need GPUs, then your absorption will skyrocket, but you can try to reduce by using liquid cooling and make it more efficient to draw energy from the server. So what about the software side? So it's intuitive that software, because the software basically holds the CPU that is varies the clock internally dynamically, so the more you ask, the more energy you will absorb. But actually, it's been studied. Actually, this is a research I published in 2009, I think. We investigated a methodology to have a meter that can be compared of energy absorption between two different systems by using a technique that was inspired by biologists. So basically, we run on a system a small program, and we use it as a meter. So we divide everything by this small program, which we called Energon back then. And in this way, you obtain fairly stable measure across different brands of servers, which is important because otherwise it's almost impossible to compare the energy absorption between two different architectures. And we noticed that, I don't want to go into the details, that's not the venue, but nevertheless, if you look at the top right chart, that is the execution of a sorting algorithm, and basically the energy absorbed is proportional to the computational complexity that computer scientists have devised. So basically, there is a clear one-on-one relation between the computing you're paying and the algorithm. So it is a good idea to invest on optimizing software to lower the cost, not just looking at the ways to lower the cost. And this is even more important if you go parallel, because if the program is unable to go parallel, basically you will run for more time and you will waste much more energy. Okay, so in general, software is a key component to ensure efficiency. So I'm not pretending to tell you lots of things about neural networks, just to give you an idea. So to understand how a software can generate information, I found that this is a good way. So basically, neural networks mimics human neurons, even though they are very far from the reality. Nevertheless, you can imagine them as a matrix. You multiply weights, there is an activation function, you go to the output, and then there is an algorithm that allows you to train, which basically means during the training phase, you want to adjust all the weights in this matrix to lower the error between the input and the output. You show the network input, output, and then you try to lower the error. That's easy. We found out that if we train a network to generate the identity function, so I give you a shirt, give me back a shirt, then you can cut down in half the network using the red neurons in the eye, and you call the first half is the encoder. So basically, he maps the shirt into two numbers in this example, and then you have the second part of the network that can generate the shirt starting from two numbers. So basically, this is an intuition of how you can generate things, because I mean, it's puzzling, at least for me, it was puzzling when I started this thing. And then you start studying also this latent vector space, as it is called, and you find that similar shirts are closer. So basically, if I start from 1.7, 5.8, and I perturbate, I get a slightly different shirt. Okay, so for reasons that are not entirely known, the network sort of cluster in the latent space similar objects. And that's one of the reasons why these things is working. And as you can see on the right part, that is the number of neurons maps down into layers, and each layer is as an amount of numbers that are called parameters. There are those numbers that you will fix for training. So during the training phase, in this very small example, you will update 100,000 parameters. Okay, 100,000 parameters in a matrix. It means that every generation will imply to go on half of the matrix in this example. So it will be hundreds of thousands of multiplication. And that's a very small example. So now, 2 more minutes, and I think I'm done. So now everyone is talking about this stochastic paradox. So if you want to have an intuition on how large language models work, they are basically learning a statistical model that is capable of doing a very simple thing, which is basically complete a text. So you provide the text, and then you ask the model, what are the most probable terms that will follow this thing? Then you roll dice, which is disturbing because we're accepting to have non-deterministic systems, and you pick up casually among the top most probable terms. And in this way, the best thing about AI is the ability to you roll the dice and say learn, and then from, and then you have to pick up between experiences, etc. Okay. The reality is that we're not doing on words. We're doing on a small group of letters that are called tokens, which typically are 2 to 3 letters. So That's the measure that is governing the AI world today, whether you are on-prem or not. And the architecture has changed over time. So in 2017, there was a paper that is really famous and important. It's titled All You Need Is Attention. And the reality is that since then, which was the LLM architecture, we started varying this thing, trying to balance the computational cost, the memory, and all the other parameters. And for instance, just to give you an example, which in France is popular because Mistral is from France, it's from Paris actually, and they did one of the first successful examples. Then the mixture of expert model, for instance, there is a first layer of a network that selects the kind of subject you want to cover and then activates only part of the network without having to activate the full network, and this will reduce the number of computations, okay? And this was basically the original model by Mistral was 56 billion parameters, 56 billion, grouped in 8 billion parameters, okay? But that's small, because if I look at models such as GPT 3.5, latest publicly announced, it was 175 billion parameters. So this means that every time you ask for a token, you multiply with a data structure which is 175 billion numbers. It's huge. And everything now is governed by the cost per token, okay? So if you look there, that's the pricing. The pricing is a good example because, I mean, people is not disclosing information about the energy, but you assume that they want to cover the costs of the energy. So actually, this is how it evolved over time. So as you can see, there is I think is for 2024 is a factor of 2, and it's expected to a factor of 5 since the beginning. The cost per token on the same class of models, of course. And this is interesting because this means that we are optimizing things quite significantly. I mean, 5x in 2 years, it's impressive. So if we look at the energy consumption per inference token on publicly available data, then you can see that more than 25 joules per token were estimated on GPT-3. 4o is estimated to be less than 2 or 3. Llama, which is an open weight model, is on the same range. Okay, so you see in few years how the cost per token has dropped. Part of it is because of the architecture. Part of it is because of the hardware architecture that runs the thing. Notice this, because in this case, the brown part is evaporated water. That's huge. That's million liters. One last comment. You may have noticed that now we have these reasoning models. Reasoning models basically use a technique that originally was called chain of thought. So basically, the model talks to itself and try by manipulating language to solve a complex problem. One may argue, so now that we are optimizing the cost of token, but we are multiplying the number of tokens we process, what's the point? Actually, new techniques for reasoning, for instance, the most efficient is the so-called chain of draft, are even costing less tokens than the direct answer. So, I mean, don't think that it's just the basic approach that everybody has become popular just a few months ago with DeepSeek R1. But since then, lots of things have been done. Okay, so I mean, I'm late, so I'm not gonna spend, but I mean, if you look at the size, Llama 3 is 400 billion parameters. If you want, you can run on-prem. It's huge. I mean, the largest we've been able to reasonably run on our data centers is 70 billion. 400 billion is not really things. So there are already results that relates the computing time, the model size, and the model size for training, because training is the most expensive phase. You may spend $5 million just for one training on 1 trillion token, okay? So huge amount of data, lots of compute, and then you get the model, and what about SLM? I mean, is a solution to run smaller models on our premises. So I did some computation on our laptops, and these are numbers that I took from running small language models. So let's say 8 billion parameters, which is small, can run on your device, and the energy used is almost 900 milliwatt hour. Okay, so it's 1% of the battery of the laptop I was using, and I use it actually the battery for measuring, which means that for a single prompt, 1%, which is 100 prompts, and then the battery is out. So it's expensive also to run on the device premises. So the distributed nature of AI, by which I mean the larger the model, the better the results, which means distributed computing across multiple GPUs, so distributed memory, push for denser components, because the denser you are, the less communication you are, the more tokens per second you will get. And that's one of the design requirements that we have to face. And at the same time, we look to optimize the joule per token in terms of energy, but it's a difficult computation, because actually when you measure the server, you're measuring a lot of overhead, the fans, the electronics, the network, etc. So it's difficult to extrapolate a reliable number. All the numbers you will find in literature tend to be gross. So don't take it as, I've seen already people say, oh, we have to do this, because, I mean, that's really gross. I mean, we probably even need new methodologies to measure this thing, because actually we're just, with an ammeter, we're measuring at the end of the server, and then we divide, and everything is done. And the efficiency also requires information that we often don't have. So that makes it difficult to optimize things. So designing a data center for the AI is basically about saving resource, because if you save resource, you're spending less, but you can also be denser, so you get both things. But nevertheless, liquid cooling is basically a requirement. Otherwise, you will be able to run really few GPUs and it will not make the difference, or run any on-prem service. So people is talking about open models, which is open weights model, because they don't release the training set, just the weights. But beware, because that's not entirely a solution. I mean, we also need the architecture to run these things in an efficient way. And as of today, larger scale models do things that are impossible at smaller scale. So I think that probably mix and match will be reasonable. And the smaller models are important also to push forward the research, because I was saying, otherwise the research will be made only by companies that have enough money to afford the development of these things. So one question is probably for the panel. Credits. So most of this presentation has been generated using GPT. So I used quite a lot of token, mostly for the charts, but I checked the source.
We don't have much time, but probably we can have one quick question from the room, if there's any. Otherwise, we will have a discussion later, roundtable discussion in half an hour. Okay, we can probably wait.
Yeah.
Thank you. So now we will move on to the second presentation from Professor Tao in Chuan. And presentation is here. Try to see.
Dear Chairman, thanks for your kind introduction. The title of my presentation is Thermal Management of Modern Data Center. My presentation will be divided into 5 parts. Finally, I will make a short summary. The data center is a collection of physical facility where digital information is processed, transmitted, stored, and exchanged. And information is processed by CPU, GPU, and TPU. And they are mounted in server. And the server is placed in rack. So rack is a very important component of data center. Heat is generated in CGPTUs while they are working and must be dissipated timely to maintain their temperature below a certain value. Otherwise, they will soon fail. Therefore, cooling is very important for data center operation. For the cooling of the entire system, it should be divided in the first cooling and second cooling. First cooling means the cooling of coolant for the electronic devices in the computer room. And this coolant should be recycled, and they are cooled in the second cooling system. So therefore, for the entire cooling system of computer room, this part we call first cooling, which is a convective heat transfer between a hot body with a coolant. And this part is second cooling, which is used to cool the coolant of the first cooling. The importance of delineating first cooling and second cooling as follows. But there are different heat transfer processes. First cooling is a convective heat transfer. Second cooling is overall heat transfer from the hot fluid to cold fluid, which is generally not too much specific for cooling of IT. The first cooling is governed by the Newton's law of cooling. The second cooling is governed by the overall heat transfer equation. In the past several decades, the technology advancement mostly happened in the first cooling, and which is a major concern of the present presentation. When you put envelope of the computer components into the sea, it mainly reduces the energy consumption of the second cooling. Only when the seawater is pumped into the envelope to indirectly cool the IT, the first cooling is also enhanced. Now let's talk about power usage, PUE of data center. In 2007, TGG gave definition of power usage efficiency as follows. PUE equal total facility power divided by IT equipment power. Obviously, to save energy, the lower PUE, the better. But regrettably, the above definition is completely contrary to its name. In conventional thinking, for the efficiency, the higher the better. But for PUE, the lower the better. The energy consumption of a data center is used in following 4 aspects. First, IT equipment. Second, cooling. First, power distribution system. Fourth, lighting. This is for PUE larger than 2. For PUE less than 2, okay, the supporting system, including cooling, UPS, building, transformer, lighting, PDU, and computation equipment in the right-hand side is about 52%. Driven by the rapid advancements in AI, global data center energy consumption has increased very quickly. There is a world average annual PUE reduced situation in the recent years. Because improvements in thermal management, PUE in 2007 is about 2.5. In 2011, about 2. And in 2023, is about 1.5. Well, now let's see some electric consumption in China and USA. In China, in 2022, the power consumption of a data center in China reached 220 billion kWh, which approximately equal to 3% of entire society. In USA, according to a report from Berkeley Laboratory, in 2024, it's about 4 to 5%. The average emission of the China's electricity used for data center is about 13.4 of the country's total carbon emission. Now, how the thermal management improved in past decades? It includes two aspects. First, progress of overall cooling framework, from air cooling to air-liquid hybrid cooling and to liquid cooling. Second progress is a chip cooling structure. This is a very simple picture for chip cooling, okay? From junction temperature to inverter temperature, we have many thermal resistance. Any reduction of thermal resistance will enhance the cooling effect. In this presentation, we will mainly discuss about the progress of overcooling framework. Finally, we'll talk about progress in this chip cooling improvements. Second part, air-cooled data center. Well, the most serious problem for air-cooled data center is the mixing of hot and cold air. This is a very idealized picture where cold air and hot air goes along its own way. But actually, some mixing may be happened. You see, the hot gas may be from the hot air to cold air. This is called recirculation. And the cold air maybe goes to hot air. This is called bypass. Okay, like this one. Here we have hot air goes into rack. After heated, it goes to the open place for return the hot gas. But some mixing may be, happened between the hot gas and cold gas. So people propose several indices to showing the mixing. Now, first we talk about front of the rack. If the inlet temperature of the rack is equal to supply temperature, then the numerator equals 0. So SHI equals 0. That means if no mixing, SHI should be equal to 0. Okay? At the back of the rack, it's the hot temperature. If the return temperature equals the out temperature of the rack, then this RHI equal 1. So if no mixing at the back of rack, RHI should equal 1. If less than 1 or larger than 1, then some mixing of hot and cold gas happens. In the recent years, air-cooled data center is developed in following 3 stages. At the early stage, we call room level cooling, okay? From very simple situation to underfloor air distribution to closed aisle, cold aisle, we can call containment, like this one. This is a typical data center structure of cold aisle containment. Then it is with the increase of scale of data center, the big air conditioner is divided several small air conditioner, which is sit between different racks. We call this one low level data cooling, okay? Now, further increase is the rack level. That means each rack has a closed air cooling loop. Hot air goes in to the back of the rack where it is cooled, okay, by a heat pipe. Then when it goes out the rack, it becomes cold. Then recircle in the inlet again. So therefore, for this kind of rack cooling, the mixing between hot and cold air is very less. So approximately SHI equal 1, S equals 0, and RHI equal 1. So this is called rack level. As soon as the power density constant at the very beginning, each rack less than 3 kilowatt, 10 kilowatt. And underflow distribution is about 5 kilowatt to 10 kilowatt. And for the low level, it's about 15 kilowatt. And for this one, about 20 kilowatt. Now, let me say some word to the heat pipe rack back cooling structure. This is the computer room. Each rack with a heat pipe system, not like this one. Heat pipe at the back of the rack, okay, where is an evaporator which cool the hot air after it cool the IT components. Then the gas go outside. The cooling here becomes condensate, and it returns again for the cooling of the rack. And the heat here is also dissipated to this refrigerant system, and finally to the environment. Okay, so that is one rack. Okay, and the heat pipe like this one. In this part, it evaporates the heat from the hot air, and then the heat is condensed in the condenser to the outside, and here to the fluid. Okay, and this is an example for the heat pipe in our notebook, and here is a cross section for the rack. Okay, this is a rack with back heat pipe cooling. Now all here are the fans for draft air, and this is the computer room. Okay. Now I will give you a special test result of a low-level laboratory data center at our university. We have a laboratory low-level data center, which has 10 racks and 6, air conditioners. And we set some couples in front of the rack and the back of rack here. Okay, this in front of rack, and also have many at the back of rack. And also we see all the leakages for the air leakage, because in the rack there are many leakages where air may be leakage or leaking. So we seal the leakages. Then we make a very comprehensive measurement of the air temperature. Totally 484 thermocouples were set at the rack front and back to measure the temperature distribution. Okay, then with such kind of test, we got the room SHI almost equal 0, 0.14, and the RHI almost equal 1, 1.005. Okay, then let's talk about multi-scale heat transfer. You see, the data center heat transfer is a typical multi-scale heat transfer problem. We call this one multi-scale system, which means at the different geometry scale, the equations are all the same. That is momentum, energy, and mass conservation. But the step of numerical simulation is very different, from very large to very small. We call this multi-scale problem is multi-scale system. Another way multi-scale process happens in the PMFC. Okay, now let's talk multi-scale system for computation. So flow and heat transfer process in the air-cooled data center is a typical multi-scale heat transfer problem. Okay, and from the whole computer room, maybe tens of rooms, meters, and to the welding point, it's about millimeters. Okay, so several other difference in scales. When we doing multi-scale simulation, we may subdivide into several stages. First, for this submodel. Second, we combine these two. Third, we combine this two. Finally, we combine this one. So when we work for the 4 levels, we can simulate the temperature of the welding point. And this is another view from bottom to top of a multi-scale problem. We have did such multi simulation for the ship data center, which has 15 racks, okay? And we divided into 4 submodels, okay? And then we transfer solution from one model to the another. So the first submodel, second, third one. okay, fourth one. Then we transfer solution from first level to second as a boundary condition, try second to third as boundary condition, find it from second to third as boundary condition, okay? So this is a way of transfer boundary condition from first level to the last level. Now we make some comparison very interestingly. For the one rack situation, please know the one rack, not 15 rack. We use a very fine grid system with about 30 million grids for the total field. So we make very detailed simulation. Another method for the one rack, we use mathematical simulation as I presented before, 4 submodels. And we compare the simulation result. You see, the predicted field maximum temperature difference is only 1.6, about 1.2%. The predicted waiting spot temperature difference is only 0.2 degrees C. Okay, but the time spent for the very detailed simulation is about 2.5 about the mathematical simulation. Okay, now then what is the heat flux limit of air cooling? This is a very typical problem put forth in 1981, but at that time no answer was given. In 2001, we gave the answer. For the impingement situation, the inlet temperature is 35, chip time is 70, and a good we were good fan available for that time. And for the sink, 80 times 60 times 50, it got the heat flux 21. If the temperature difference increase to 65, then we may have heat flux 39 watt per square centimeters. Okay, of course, this cannot satisfy the requirement for ever increasing power requirement. So liquid cooling technology has stepped on the historical stage. Now let's go to third part, air-liquid hybrid cooling technology. Now first, we should say some words why liquid cooling can increase heat flux and save energies, okay? This is because from first cooling, the physical property of liquid are very favorable to enhance heat transfer. We can use FOM to show the effect of the physical property, okay? And this for the convective transfer in the tube. For this water, this is 85,000. For fluorinate, it's 21,000, but for air, it's only 161. Therefore, heat transfer coefficient of water and fluorinate is much higher than air cooling, coefficient. Because the high heat transfer coefficient, so the required flow rate of liquid is much less than that of air. Therefore, the pumping power of liquid is much less than pumping power of air. Another effect is that because the required temperature for the liquid cooling is much less than that of air, therefore, TF can be increased, say, from 20 to 30 or 40s. Then, because the TF is cooled by second cooling, which is a refrigeration system, then the condenser and evaporator can work at a higher temperature. We know that the increase of condensation or evaporation temperature will increase COP. That's reducing the consumption of compressed power. Therefore, because these two reasons, so liquid cooling can save energy. Now, presently, there are 3 liquid cooling technologies, okay? Liquid cooling, air, hybrid cooling, okay? And single-phase immersion cooling and spray cooling, okay? And finally, two-phase cooling. For the first hybrid cooling, we have 3 exact problems. First, liquid cooling, the high heat flux caused by cold plate. So cold plate the sinker design. Second, the coolant selection. What is the coolant for cold plate? Third one, the module rack manufacturing and setup ways, okay? First, we talk about the cold plate design, okay? Well, along the flow line, the cold plate has 3 different parts. That is inlet, outlet of the coolant. Second, the manifold topology, okay? This is manifold, we have different manifold type. Third one, channel shape and configuration. So by the three factors, we use DOE. We got a 26 new configuration and make numerous simulation by this kind of equation, okay? This is a grid independent examination. And this is pressure difference for 26 new cold plate. And this is the best one of number 20 number, okay? And we compare the pressure drop for the 26 cold plate. We find the smallest pressure happen for the 32. For the 30 cold plate, the inlet outlet are both at center lines, okay? And we also make experiment validation, the agreement between the test data and measure the one are particle within 5%. And also we make performance evaluation. We take temperature difference and the pressure are both in consideration with weight 5.5. Then Trinity number plate is the best one. We have further defined the Trinity number plate by defining the channels, okay? Finally, we got a cold plate, which keeps the chip temperature 85 with average velocity 0.41 meter per second. The heat flux can be increased to 266 watt per square centimeters. And the pressure drop only 18 kPa. And the ratio of K over delta X, delta P is 14. Compared to Turkmen P's in 1981, it's only about 3.6. Second problem is the cooling selection for the cold plate. It should require several conditions by heat transfer, anti-freezing, non-toxic, and so on. Okay. Now, usually, now in China, the three big companies, Huawei, Inspur, use ethylene glycol or propylene glycol. Now, the modes for supplying the rack for the hybrid cooling, there are two modes, one integrated rack, second a decoupled rack. In the integrated rack, the server and its air cooling, liquid cooling system are designed as a whole. The advantage is a high integrate. Disadvantage is a less flexibility and universality, okay? And the technical barriers are prone to exist among different manufacturers. This is the integrated rack in China mobiles, okay? Here are a lot of quick plugs for water cooling water, and here are different racks. This is a server, okay? This two are cooled by the cold plate, other component by air, okay? And this is another integrated rack provided by Zhongxin, a telecom equipment. Now, another part is the decoupled rack design in hybrid cooling technology. It has two advantages. First, providing greater flexibility for the user side. Second, decoupling makes the entire system being more wide box. So it can towards, okay, standardization, economy, and scale. Okay, that is decoupled rack, which is open, okay? And this is the front view of decoupled rack. And this one is filled with server by users. And this is the air and liquid cooling system in the decoupled rack. This is system for the cooling air, and this is for cooling water, okay? And the cold plate will cool by water. It's become from 40 to 50. And this water is recooled here. And the heat is finally brought to the cooling towers, okay? And this is the detail for the air cooling heat transfer, heat exchangers, okay? And this is the control system, okay? This RMC can control central management of the water and electricity information for the liquid cooling. And this is another one is CDU. Here, first cooling, second cooling exchanges their heat here. And finally, the heat was brought to the environment by the second cooling. Fourth, emerging liquid cooling technology. First, I give you some example for liquid cooling, immersion spray cooling. First, spray cooling of Guangdong Heyi Company. Here is a spray cooling. You see, the cooling to go the top from down to the components and chips. This is a data center equipped by the spring cooling. The coolant is a special kind of oil. And on a small scale, commercialization is realized in China now. Secondly, immersion cooling, okay? And this is schematic view presented by nature. And this is a picture in Ali data center, okay? Each one is a box within which many servers are placed, okay? And this is one box. Within the box, many servers with one U or 4U. After 3-year operation, they found that the failures caused by humidity, vibration, and dust were greatly reduced, totally by 50% compared to air cooling. Okay. Now, here is a laboratory to face immersion cooling, okay, given by also in Singapore University. And they found that the two-phase cooling is about the PU about 1.15. Okay. Now, the requirement for the cooling is very important because all components were placed in the box. So it has a suitable thermophysical property, suitable electrical property, suitable compatibility, suitable material safety, suitable environment influence, low ODP rate or GDP, okay, GWP, and total cost should be acceptable. In my understanding, before the advent of such a cooling medium, it will be very difficult to achieve a large-scale commercialization of commercial cooling. Now, fifth part, development trends for energy saving and the low carbon technology of data center. Cooling technology for ultra-high heat flux chips since 1981. We know that in 1981, Turkmen Keys proposed microchannel sink with such high heat flux but such high pressure drop. Then in 1991, Harper and Iniger proposed a manifold microstructure, which reduced pressure drop, increased heat flux. And since 1981, many improvements for the manifold were proposed like this one. And in the year 2020, in Nature, published a paper by Up and al. They say that the channel of the inlet coolant should be reduced because the flow rate is reduced along that direction. And the hot channel should increase in flow direction, and which reduce pressure drop and improve the uniformity of flow rate distribution. And recently, Tang et al. Proposed a structure by microfin, and they reach 1,000 watt per square centimeter. And our group further improved this structure and got a very interesting result. Heat flux 1425, pressure drop only 9,000 Pascal, that 9.7 kPa, and max temperature is 82. Because paper is submitted, so I have not published, so I cannot give you the structure. We use this kind of technique in another way. For many chips here, there's 2 or 4 low power chips. Total power is about 1,000. By using the structure suggested by Nature and all and make some improvement, we greatly improve the temperature uniformity and the average temperature. This one temperature clouds before the improvement. This after improvement, we reduced the average temperature by 2.6 and the uniformity improved by 2.7 degrees C. Second, the utilization of data center heat. It's some difficult in mismatch about temperature, about the supplier and the consumer, about the area. But recently it was solved by using, this heat to connect with the city public utility company. That solved the problem. For example, the PA10 data center in Paris When operating at a full capacity, it will generate 6.6 megawatt of the energy, which is sufficient to supply the needs of over 1,000 households. During the Paris Olympic, it has also used to supply hot water for swimming pool. Third one, AI-assisted thermal management of data center. I just give you some example. One example is Google and DeepMind. They use the data by and training the data of measurement by deep neural network. So improve the management, reducing the cost of data center by 40%. Another one is air cooling of Huawei. Okay, it can reduce PUE by 8 to 15% and save 27% million kilowatt hours of electricity for long-form cloud data center. Third one is our group combined with Alibaba data center. We use neural network combined with the CFD. Okay, that is a schematic picture. That is a result. Predicted and true temperature are close to each other very well. Third one is use hydrogen energy for data center. We propose a comprehensive energy system for data center like this one. Okay, and this detail one presented by paper which we present in this conference. Okay, and then for the 300 kilowatt IT load. Okay, we finally computed the PUE is 1.15, and also for this 3 kilowatt data center supplied by hydrogen energy, the reduction of CO2 is about 2,187 tons per year. Fifth problem is development of qualified coolant for immersion cooling. I say that when the qualified coolants are available, the large-scale commercialization of immersion become impossible. Okay. Finally, a short summary. You see, on one hand, liquid cooling technology is booming in various countries around the world. On the other hand, air cooling technology still has application due to its simplicity and easy of implementation. Perhaps the coexistence of various cooling architectures, each functioning within their respective applicable advantages, is a colorful picture of data center cooling technology in the foreseeable future. Finally, I would like to show my sincere thanks to many of my friends to give me during the preparation of this PPT, including China Mobile, Huawei, China CDCC, Alibaba, Zhongxin, and many of my colleagues and students in XJTLU. Thank you very much for your attention.
Reduce the number of training cycles. So quite quickly, we moved from a world in which the training was king, and the idea was, okay, we have to provide new knowledge all the time to these models, in a world in which basically we inject the information inside the prompt that is called RAG, R-A-G, which stands for Retrieval Augmented Generation, which is basically allows the model to manipulate not only the user prompt, but also additional information that typically is not present. So what Google and these big players are doing, for instance, in the search, is basically injecting the information they crawled using search engines into these things to answer. This has a number of consequences. First of all, prompts that the model process are much longer than you might think. Because you may think, what are the news today? And then you don't see that Google is injecting new information on your behalf. And at the same time, this implies that the number of token processed will grow over time. And it's an open problem. So, but basically, it all revolves about this mixing all the new technologies. So now in Excel, you can have Copilot, in Google Docs, you can have Gemini, etc. And basically, we are introducing a lot of cycle of taking information generating a prompt, trickle back in the thing. And this year is becoming popular the MCP, the Model Context Protocol, which is basically the ability of machines, of AI, to invoke actions to machines. So basically, not just manipulate text, but also actuate, which is scary to some extent. I'm not sure I'm trusting enough this thing.
We also have a comparison of two other cases which seem, for me, more complicated. For example, you make a translation by Google Translate. You can also ask AI to predict the result of a football match according to the very recent situation, health condition of footballers. 2031, in 1 week, we will have this big match between Paris and Milan. And you're Italian, but you're in Paris, so can you please explain that? So in this specific case, could you please explain what is the information flow? Where is the data center that will be used for this calculation?
So for the forecast, there are already scientific evidence that, of course, the AI is not better than us at predicting things. So the data centers, it really depends the model you're asking to. So that is, if you're asking to XAI, probably that will be in Colossus super mega data center built by Elon Musk recently. If you ask to Microsoft, that will probably be in Europe on Azure servers. If you ask to Gemini, in one of the Google data centers. And this is only partially known because they are load balancing across the globe the requests. Then you have this macro region mostly for privacy reasons. GDPR in Europe imposed a number of restrictions, so it is preferred to run AI workloads in Europe for European people. Also, OpenAI, for instance, last year opened in Ireland exactly for this reason. Some part of the workload for enterprise and education now is by OpenAI is run in Europe and not in the US.
So that depends on the specific model that you will use, right? So the second question is still for you, Antonio. You already explained a little bit why we are densifying everything from the chips and until the rack. You told us that we put more and more GPU on the rack, and this rack is consuming more and more energy. So what is the fundamental thing? What do you think that in the future you will have several hyper or giga data center per country, or probably we can share one within Europe?
So that's an open question. If I look there are several aspects that we have to take into account. I think that somewhere, at least in Europe, there is still some IBM AS400 already running. Okay, it's a very old technology, but it was an IBM mainframe, and it was super efficient because everything was designed by a single vendor. Then we changed and we said, this is lock-in. We need to have more composable things. We defined electrical specification protocols, I2C and everything, so that you can have a computer built by multiple vendors. And that was basically the PC era and the 80s and the 90s. Now we are, to making things more efficient, we are sort of going back. And NVIDIA is now IBM to some extent. If you look at modern server, it has been mostly designed by NVIDIA, and the rest is the box and a few other buttons provided by the vendor, which is becoming a problem in terms of costs, for instance. So I don't think, so that's one part. So every interface will introduce overhead. I mean, there's no way. It is more composable, it is more nice in many ways, but at the same time, if I look from a resource standpoint, there will be overhead, it's known. On the other hand, there is the geographical location. Because, I mean, cooling is not about, politics, it's about temperature. And so, and the paradox is that, for instance, Italy is a bad country to make data centers. Not because we got hot. I mean, among the best place where you can get a data center is a desert. And it's because, I mean, it's a fairly stable climate cycle. So you can optimize using physical principle for that particular night and day shift, etc. In Europe, in Italy especially, we got up to 50 degrees Celsius of temperature excursion between the winter and the summer. And so it's difficult to design. And at the same time, there are geopolitical considerations. So first, I mean, I want my data close to me, and so we have to accept that. We also have military consideration to be done, because if you concentrate everything in a single place, a single missile is enough to shut down everything. So if I look at the strategy of the big players, they implemented in the beginning, mostly in the north of Europe, for instance, Microsoft, Google, also for tax reasons. I forgot tax reasons. I mean, Ireland is still hosting a number of data centers, mostly because it was zero tax at then. So they started like this. Now they are spreading data centers all around. And I think that in general, the distributed solution seems to be more manageable, because otherwise they were spending a lot of money. For instance, the big data center of Microsoft, which I know best than others, they have their own network, global network, plus 5 different network providers that are just backup providers, and they have to prove that they are separated, so that in case of failure of one, you still have the other, and the same applied for energy. So the more resources you concentrate, the bigger is the impact of the fail. And so I don't think that is realistic. Already, it wasn't for business reason. If I look for resources, how much energy density we can provide in a single point of the grid? That's another big question, because now we're talking about gigawatts, not anymore. And so the risk is that the grid is simple. So for instance, in Pisa, our data center can grow up to 1 megawatt. Then we check it, and to have 2 lines to 2 different power stations, we need to pay quite a lot. So we have also to take into account that part, because now we're talking about amount of energies that are comparable to a town. And so if you deviate from the grid that much energy, you have to compensate somehow.
That is why some huge data centers are using their own power generation plant just beside. So we are moving on. Yeah, the next question is, Professor Tao has talked about air cooling and water liquid cooling. So I would like to know, what is the physical difference between air cooling and water cooling, Professor Wang, from the heat transfer point of view?
Yes, actually, air and water is quite different. We can explain in for example, the advantage of liquid, typically water, and cooling water. The over air cooling using maybe we can consider some difference from different aspects. For example, the heat capacity for energy storage per kilogram per degree C is quite different. For example, water is about 4,000 and air is 1,000, which is actually more than 4 times per kilograms than air for each degree. So this means it can absorb more heat before getting hot. And the second one is we are always talking about the density between water and the air. Everybody know water is about 1,000 kilogram per cubic meters, but air is only about 1.2. So which is about more than 800 times, and so it can carry very fastly more heat. And the third one is about volumetric heat capacity, which heat can carry about per meter square per degree. Water is about 8 megajoules per cubic meters and per Kelvin. And air is only about 1.2 kilojoules, which is actually more than 3,000 times. So that's why a very small flow of water can remove as much heat as a huge volume of air. So this is different. And the fourth one is about the thermal conductivity of air and water. So water is about 0.6 and air is only 0.025. It's again, it's about more than 20 times faster than air. So make it more difficult and more efficient for heat transfer from chip to fluid. So thank you.
That means for dense racks, the only solution will be liquid cooling, right?
Yes, liquid cooling would be much better.
Okay.
Yeah.
Thank you. So to finish this part, this is one of the solutions that I found from the internet. This seems to be a radiator heating rooms, but it's actually a server. So people can buy or rent this server. They have free heating, and there's a company that will use this server to make computing. So I would like to know, is this solution could be the future of, or one of the future alternatives to balance heating, thermal management, and also the power of computing?
Yeah, actually, sometimes this is a very smart idea. I think sometimes we need heat for our housing, so we can use the heat for it's a kind of waste heat recovery. So this is we don't have any CO2 niche, and also we can reduce the waste and show how digital technology and heating can work together. So I think this, we can see, the server also generate the servers generate heat. This heat can be used especially for some cold region, But of course, if for some warm region, maybe it's quite difficult to use this technology because we need a lot of heat and the environment is with high temperature. So we need to overcome consider some issues. For example, less useful in some summer and warm areas, and we also need to have some balance between the computing and the heating demand. So sometimes we through a thermal control system. So we need to have some balance between we are because the most important thing we need to let the AI, the data center with the AI system work. This is the first issue we need to consider, and then we could consider how to use the waste heat. So the first thing we need to let the computer system work well, and then after this, based on this consideration, we can only consider how to use the waste heat. Thank you.
Good, thank you. So typically, this system cannot be used in Pisa probably during summer.
Yeah.
Okay. Good. To finish, Antonio, you said that the design is really challenging when you have a very difficult condition during the day and the night. So you need something very stable. But I think that is why we are here. We have specialists working on heat storage. We have several keynote lectures this afternoon, and we have one of the colleagues from Norway, I guess, George, are you here? And who will make this keynote about the storing code with ice, and we use ice during the day. So so thank you, both of you, and thank you very much for your attention. I think we will need a coffee now, and we're coming back here at 11:30. Please, thank you very much.